Okay, we're going to jump into chemical bonding here. We're going to start talking about chapter 6 in your book. And so for your final, uh, you're going to cover chapters 1 through 6. And so we'll talk more about that in class. But I did want to go ahead and get you guys caught up on what we talked about today in class via lecture. So we're going to start here with chemical bonding and go through that. Let's see if I can make this full screen for you. There we go. Chemical bonding. A bond is something that's going to result from the attraction of nuclei for electrons, right? And so basically we talked about those electrons, right? And those outermost electrons would be called your valence electrons. And so they're the ones that are going to be involved in the bonding process. All atoms are trying to achieve a stable octet. As you recall from previous lectures, an octet means they're trying to get to 8 valence electrons in the outermost regions or the outermost layer. In other words, what we're saying is that the protons in one nucleus are attracted to the electrons of another atom, right? And so we're going to see something now be put into play called electronegativity. That means the more electronegative they are attracted to each other more intensely. And so you're going to see that as we go through. And if I go a little fast here for you, just feel free to push pause or go back and rewind it, whatever you need to do, okay? All right, we're going to skip the little joke there and go on to 2 types of bonding. First one we're going to discuss is called ionic bonding, and this forms ionic compounds. You'll notice that there is only a transfer of electrons here. Transfer, right? There's a winner and a loser of those electrons, and we'll look at that more closely in just a moment. The other type is called covalent bonding. They form molecules, not compounds, and in covalent bonding, they actually share electrons. And I did a little exercise with them on the board earlier today with the word covalent. Covalent itself gives you the definition of what the term means. If you were to take the word covalent and subdivide it, put a slash mark between the word co, or the prefix co, and the word valent, right? The word co, if you think of words like co-pilot, a co-ed dorm, right? Those things mean a co-pilot means that you are sharing control of the airplane. A co-ed dorm means that there are both males and females that live in separate floors of that dorm in college. And so the prefix co literally translates into share, right? So anytime you see the word co or the prefix co, it literally means to share. Valent, right? Remember is just referring to the word valence electron, right? So co literally means to share. Valent is talking about the valent electrons. So we're really sharing valence electrons, right? That's what the word covalent in itself means when you break it down. So I find that very interesting. The term itself can tell you exactly what's going on. Okay? There is another type of bonding that we'll discuss. It's called metallic bonding. In metallic bonding, what you see is that's going to occur between like atoms of a metal in the free state. What you're going to see is that the valence electrons are very mobile in a metallic bond. It means they are free to sort of move about. I use the term kind of leapfrog over each other. So maybe as a kid, you play a game of leapfrog. That's kind of what the valence electrons do. They can kind of just move freely over top of each other. And this becomes very important in just a moment when I get there. We call this mobility that takes place a sea of electrons. And much like sea, the water droplets roll over top of each other, right, in water. It's the same way here. Those electrons are going to roll over top of each other, right, in sort of a free state. This is much different than what you would see in an ionic compound. Metallic bonding, metallic properties are very characteristic. So here are some of those properties, and you'll need to note these. I'm going to go over some of the definitions. You will not see the definitions listed for you on this page, so you'll either have to look up the definitions in your book, or you'll have to pause as I go through and give you the definitions. The first characteristic is high. It says MP temps. MP stands for melting point, right? So metallics or metals have very high melting points, temperatures, right? In order to melt these guys, you've got to get up to very, very high temperatures. The other term you see listed is ductile. If something is ductile, that means that you can pull it or draw it out into a wire, right? I used the example in class today of if you've ever been to Gatlinburg and you've walked the streets where they make candy, you'll see people that are making saltwater taffy, and they start in these big balls of saltwater taffy. They kind of look like a big basketball, right? And then they put them into this machine, right, called an extruding machine, and it rolls it down. And so it goes from this basketball size, right, till it gets rolled down into about the shape of, say, a roll of paper towels. And then they keep rolling that, and it gets skinnier and skinnier and skinnier until it comes out to like almost a snake size, and it goes down to almost like a pencil size before they cut it off and wrap it up. So ductile means we can pull that out or draw that out into a wire. Malleable means that you can hammer it into a thin sheet. What I did in class, the demonstration I did, in case you missed it, was I took a spoon, a normal spoon, and I hammered it out so that spoon was entirely flat. Okay, so malleable means that it can be hammered into a thin sheet. The other term you see there is shiny. Shiny, you might also see the term luster or lustrous applied to that, and that just means it's going to be reflecting light. Okay, so very important terms for you to know. The vocabulary is important. Either pause and go back and write down what I've explained to you, or you can look them up in a book, although you may find my explanations more easily digestible for you. The other thing about metallics is that you know they are hard substances. That'll also come into importance later. And they are great conductors of heat and electricity, right? And you'll notice it says as an S or an L, right? That's an L there. And we're talking about phases. So think to yourself, well, what phase starts with an S? I'm going to give you a second. Hopefully you said solid. And so now when you're seeing the word L or the L in parentheses, you're thinking of the word liquid, right? So when they're in a liquid or a solid phase, they are good conductors of heat and electricity. I did a very unique demonstration with a light bulb in class. I don't really have a good way to demonstrate that via this program, but if you'll remind me, I can go over that with you again or try to review that again for you guys. So we talked about those electrons, right? The reason metals are able to be like malleable and conductible and ductile, right? Well, the reason for that is because they are mobile electrons that enable the metals to conduct electricity, to be malleable, right? To be ductile, all of those things. The reason is because we have mobile electrons that can kind of leapfrog over each other. So like I said, the electrons are negative. So if you watch one go over positive, right, that's kind of leapfrogging over. And so they don't really break. That's the big advantage to a metallic bond is they don't break. Okay? But when we get into ionic bonding, again, reviewing the fact here that they're transferred, right? The electrons are transferred between your valence shells. Ionic compounds now, we're going to see that yes, they're made of ions, and so they are compounds. They are not molecules, and that ionic compounds are often going to be referred to as salts or crystals. Okay, salts or crystals. Again, I did a really good demo in class where I took an ionic compound, all right, it was calcium chloride, and took a little ball of that out and I smacked it with a hammer, right? And because they are salts or crystals, they form in what we call crystal lattice structures. And so when you hit them, right, they aren't malleable. They don't flat out to a thin sheet. What they actually do is they break, they shatter, okay? Because in ionic bonds, we don't have that sea of mobile electrons, right? They are all very rigidly stuck together. Remember that ionic bonds are always formed between metals and nonmetals. We learned two terms previously back in this course. All the way from August up until now, we've used this term interchangeably. So hopefully you can remember for metals, right, the term would start with a C. For nonmetals, the term would start with an A. Okay, so for metals, hopefully right now you're thinking, oh wait, what's a metal? Right? Metals are cations, and nonmetals would be anions, right? Notice that they both have the word ion in them because we're talking about ionic bonding, okay? The metals, we talked about previous slides, somebody's a winner, somebody's a loser. The metals will always lose the electron. The nonmetals will always gain an electron. Make sure you know who the winners and the losers are. Very important to know that. Write that down in your notes. Ionic bonding, right? Also, we start to look now that there are electronegativity differences, usually of 2 or less. I'm going to give you a whole chart in the next day or two where we can look at that and look up some guys. We'll do some electronegativities, but right now just kind of know the facts that are on the screen here. We also are going to get introduced to something called polyatomic ions, right? Very important. We'll get back to that as well. Here, what I want you to note in this screen is you see sodium and you see chlorine. Before any movement occurs, if you'll count the number of electrons, you'll see 7 electrons around chlorine. If you look at sodium, you'll notice it has 1. This corresponds with your charges on your table. If you take out your periodic table, you look at sodium, sodium has a +1 charge. If you look at chlorine, chlorine has a -1 charge. It means it's missing an electron to get to the octet, right? So what happens here is sodium has an extra one. It's going to donate it over, and then when it donates it over, chlorine then achieves the octet. It gets to 8 in its outermost ring. Sodium, by giving up 1, also gets to 8. Notice that when the 1 disappears and goes over, it's left with 8 on the outermost level as well. But keep in mind, they are sharing those electrons. Properties of ionic compounds. They're a hard solid at room temp. Room temp is 22 degrees Celsius or around 72 degrees Fahrenheit. They have high melting points, as we talked about. They are poor conductors in solid phase, but they are good conductors in liquid phase. This is not like we were talking about with metals. Metals are great conductors in solid or liquids, but ionic compounds are only good conductors in the liquid phase, dissolved in water. AQ means aqueous, right? Keep in mind, when we talk about ionic compounds, we're talking about salts and crystals. That's all we're speaking of. Okay, covalent bonding. Notice they're not compounds, they're molecules. They have pairs of electrons that get shared. Remember, covalent means to share valence electrons. They have an electronegativity difference greater than 2, and they're going to form polyatomic ions. We'll talk more about that at a later date, right? Properties, I'm trying to get under my 15-minute mark here. They have low melting points and boiling points. They have very soft solids as compared to ionics, and they don't conduct electricity in any phase, right? Molecular substances, covalences, do not conduct electricity. Ionics conduct electricity in a solid or liquid phase, and metals conduct it in a liquid or a solid phase. And this is where we're going